field due to a spherical shell of charge. Now, I've been using my basketball very often. Now, you know that if you cut this ball open, what is inside? Well, inside you have air. So this is a shell. That means it is a very thin shell. Those who have cut open a basketball will know. This is a spherical shell. What is the electric field due to this spherical shell? We're going to look at inside the shell and outside the shell. Well, you know what the electric field at the surface of the shell is. Well, you must be clear about this. Now, if you charge this shell, the electric field at any point on the surface of the shell will behave as though all the charges on the shell is concentrated at its center. And therefore, the electric field at any point on the surface of the shell will be kq over r squared, where r is the radius of the shell and q the total amount of charge the shell carries. And what will be the direction of that electric field? We talked about that in the last class. The direction of the electric field will be at right angles to every point on the surface of the shell. Alright? So, the electric field at a point on the surface of the shell will be kq over r squared. We will now use Gauss's law to find the electric field at a point inside the shell and the electric field at a point outside the shell. Alright, let's do that. What is the method in using Gauss's law? Remember, the standard method is, if you want to find the electric field at a point, we take a Gaussian surface that contains the point. Alright, that's what we're going to do. Consider a spherical shell of radius r that has a total charge q. Now this is a spherical shell of, well, the spherical shell is the yellow colored, and it carries a charge positive q. The radius of the shell is r. You can see inside the shell it is hollow, and that's why it's called a shell. Now, by symmetry, the field due to this charge must be radial, and its magnitude depends on the distance from the center of the charge. So, as you move away from the charge, now here, this is the shell, and we want to find the electric field at any point outside at a distance r. And you know that as you go away from the shell, the electric field will become weaker. Is that right? And that's what this sentence means. By symmetry, the field due to the charge on this shell must be radial. What's that mean, must be radial? Radial means directed along the radius, and that's what I said, it'll be at right angles. So it will be, the field will be directed along the radius, will be radial, and depends on the distance r of the point from the center of the shell. Alright? To find the electric field E at a point, we need to find the electric field, say, at this point. What do? We construct a Gaussian surface, which is the sphere. Now, this blue sphere, or blue shell, another shell. Now, I want to find the electric field at this point due to the charge on the shell. So what do? I construct a Gaussian surface, which is a shell of radius equal to this r, because the point is at a distance r from the center of the shell. We construct a Gaussian surface, which is a sphere of radius r, such that r is greater than the radius of the shell. And now, we have constructed now the Gaussian surface. What do you now do? If ER is the field at the point, E sub R stands for electric field along the radius. Is that right? Along the radius, which is actually at right angles to the surface of the shell. So if ER is the field at this point, at a distance r from the spherical shell, then what is the net flux crossing the Gaussian surface? Now the Gaussian surface is a shell of radius r. What is the area of such a sphere, a spherical shell? What is the area of a sphere? Is 4 pi r squared. So if E is the electric field, means the flux per unit area is E sub r. So the net flux, the total flux crossing the Gaussian surface will be the total area, which is 4 pi r squared, multiplied by E sub r, which is flux per unit area. So the net flux crossing the Gaussian surface will be E multiplied by the area of the Gaussian surface, 4 pi r squared. Alright? Now, according to Gauss's law, this net flux must be equal to what? Must be equal to Q inside divided by epsilon naught. But according to Gauss's law, phi net must be equal to 4 pi k times Q inside, which is the same as Q inside divided by epsilon naught. In this case, this is more convenient because of the 4 pi in the phi net equation. Because these two are going to be equal, is that right? The net flux leaving the Gaussian surface equal to 4 pi k times Q inside. So we take these two and equate. ER times 4 pi squared equal to 4 pi k times Q inside is the amount of charge carried by the shell. And all that charge is inside the Gaussian surface. And therefore, this is the charge carried by the shell. Now, therefore, what is ER equal to? ER equal to KQ divided by R. Isn't it interesting? ER equal to KQ divided by R squared. In other words, when you charge a spherical shell, if you want to find the electric field at any point outside it, the charge on this behaves as though it is a point charge. Isn't this the point charge equation we had derived some time ago? Electric field at a point E equal to KQ over R squared. What it tells you is that the charge on this shell behaves as though all of it is concentrated at its center. Now don't confuse here, charges are not inside the shell. Charges are actually outside. But the equation for the electric field suggests that the behavior is as though all that charge is concentrated at the center, so that E equal to KQ over R squared. You remember in the beginning I said, what is the electric field at the surface, at any point on the surface of the shell? The electric field at any point at the surface will be KQ over big R squared. For the surface, the distance of any point on the surface from the center will be that radius. And as you go away from the surface, as R increases, the electric field will keep on decreasing. So the maximum electric field is at the surface. As you go away from the surface, the electric field decreases. And now, this is the same as if you use k equal to 1 over 4 pi epsilon naught. It will be 1 over 4 pi epsilon naught times q over r squared. What does it tell you? It tells you the electric field varies inversely as the square of the distance from the center of the shell. Alright. What is the field at any point inside the charged shell? Now, the equation we derived in the last slide was the electric field at any point outside the charged shell. If you now go inside the charged shell, how do you find the electric field inside the charged shell? Well, if you take a Gaussian surface inside the shell, is it possible to take a Gaussian surface inside the shell? What will be the charge inside? Is there any charge inside the shell? No, there is no charge inside the shell. Charges exist only on the shell. There is no charge inside the shell. Inside the shell it is, well, not empty space, but there is no material there to hold the charge. So if you go inside the shell, there is no charge inside the shell. So if you take a Gaussian surface inside the shell, there will be no charge inside that Gaussian surface. What does that mean? Since there is no charge inside the shell, there is no flux crossing the Gaussian surface. You see? You take a Gaussian surface inside the shell, there will be no flux crossing the Gaussian surface. Why? Because there is no electric charge inside there. Therefore, the field at any point inside the charged shell will be zero. There will be no electric field inside a charged shell. Can you believe that? In fact, many scientists refuse to believe this. It was Faraday, a scientist called Faraday, who first proposed this. He said if you take a shell and give it any amount of charge you want, there will be electric field on its surface, there will be electric field outside the shell, but he said there will be no electric field at any point inside. And many people refuse to believe it. Many scientists refuse to believe it. So you know what he did? He constructed a big spherical shell and went inside of it and stayed there. He put a chair in there and stayed there and started doing his work. And he asked his assistants to put large quantities of electric charge so that it began to spark outside. You couldn't go anywhere near it because it carried so much of electric charge. And Faraday was comfortably reading inside, not even knowing what was happening outside. There is no electric field inside a charged shell. Inside a charged shell is shielded from electric field. That is a beautiful result. So inside a charged shell, there is no electric field. So if you look at this, where is the electric field maximum? The electric field is maximum at the surface, at any point on the surface of the shell. That's where you got the maximum electric field. Now, inside, anywhere inside, there is no electric field. And as you go away from the surface, the electric field decreases as 1 over 4 pi epsilon naught times q over r squared. This is the behavior of the electric field outside the shell. And at any point on the shell, the electric field will be kq over r squared. Alright, let's do a problem. A spherical